This is our first lesson about chemical reactions. So in the last unit we learned about ionic and covalent compounds, and now we're ready to mix those compounds and get them to produce new products. We're going to look at a lot of videos of some reactions today to kind of get a picture of what a chemical reaction looks like. But by the end of this lesson, you should be able to know what a reactant and a product is in a reaction. In other words, I might say to you, hey, name a chemical in this reaction that is a product, right? And also be familiar with these symbols that chemists use to write chemical equations, which are designed to save time. But of course, if you're going to save time by using this shorthand, you got to know what those shorthand symbols mean. So let's look at this reaction. So what's going to happen here is we're going to watch somebody add aluminum foil to liquid bromine. So that's pretty cool. We get to see what, I think we know what aluminum looks like, but we get to see what liquid bromine looks like. And it's going to produce aluminum bromide. Well, so I think a lot of this you might, well, there's the liquid bromine, by the way. Doesn't that look really cool? The element bromine is red. It's very beautiful. Aluminum foil, you know what that looks like. But you notice that aluminum and bromine, those were like the ingredients. It's like if you're making cookies, that's the butter and the sugar and other stuff that goes into cookies that I don't know. But the aluminum bromide, that's the thing you make at the end. That's the actual cookies that you've made that you pull out of the oven. If you're wondering what the aluminum bromide looks like, that's what this looks like. Smoke. It's not really smoke. It's a powder. It's aluminum bromide that's been made by this reaction. Hey, by the way, this reaction, you saw all the sparks, and I bet you if you touch the test tube, it'd be very hot. It gives off a lot of heat. It's referred to as an exothermic reaction, right? But all of this smoke is not actually smoke, it's powder. Watch. If we let it keep going, you see how the powder is coating the tube on the inside? That's the aluminum bromide. Now, as I said, chemists do not like to write this out in words. They'd prefer it to look this way, right? Aluminum is added to bromine to make aluminum bromide. This is the stuff at the end, right? And this sort of shorthand version is referred to as a chemical equation or a chemical reaction. Now, I tend to refer to it as a chemical reaction because if I say equation, a lot of times people think math, and it turns out that these symbols do not mean what they mean in math. But you will use those terms interchangeably. Chemical equation, chemical reaction, and very rarely do chemists write wordy versions of it. Usually it's in the form of symbols to save a little bit of time. Now that means we got to know what those symbols mean. Now I think you know that the aluminum and the bromine and the aluminum bromide, those are the chemical formulas for those chemicals. And we actually know how to write them, checking charges and all that kind of stuff. But what about the S, the L, and the S? Well, those things are referred to as state symbols. I might say to you, be sure to include state symbols on an equation. And what that means is those are describing the physical state of that substance, and they're not complex. You remember in the beginning that bromine was liquid? That's why it has an L. Its state symbol is L because it was a liquid. The aluminum foil was a metal. It was a chunk. It was definitely a solid, so hence the S, right? So solids, anything that's a metal, a powder, anything like that, will have an S. And it will always have an S. If it's a powder, it's still S, not P, right? And the aluminum bromide, which was a powder, is a solid too. So we have liquids and solids. Any guess what symbol we'll use if it turns out the thing is a gas? You're right, it's just going to be a G. So we have solids, liquids, and gases. Those are the state symbols we could see. But there's also this one over here, this thing, this AQ. And that fourth one is a little trickier. Now it didn't show up in this reaction because there was nothing aqueous. That's what it stands for. But I'm going to show you a reaction that has something that's aqueous in it in the next one we look at. But state symbols simply describe what the chemical looks like, and there's only four of them: solid, liquid, gas, aqueous. The other thing that you got to know about chemical terminology is it matters what's on the left and what's on the right. The reason there's an arrow here is because chemical reactions are written as a storyline. The stuff you have in the beginning, the ingredients, the stuff you have to bring, right? Did you notice that the chemist had to bring the bromine and had to bring the aluminum? The ingredients chemists refer to as reactants because they do the reacting. We didn't have to bring the aluminum bromide because we were going to make it during the reaction. The thing that you're going to produce is a product. So if you were the Ford Motor Company, a steering wheel wouldn't be a product, a tire wouldn't be a product, none of those things, those components would be products. The car or the truck is the product. But the steering wheel and all the other little components are the reactants. So we have reactants and products. So I may say to you in a minute, what's a reactant in this reaction? And the answer would be either aluminum or bromine. Both of those are reactants. What's a product? That's the thing that you as a chemist didn't bring. So it's the thing that's got to be made and will be there at the end of the reaction. All right, so two other symbols. This plus sign does not mean add. Sort of, right? What it means is that aluminum was mixed with bromine or combined with bromine. Now, the words could be a bunch of different ways, but it's just saying you're mixing those two. And very often you could say the opposite. Bromine was mixed with aluminum. But if you look up my description at the top, I did not use mixed with or combined with at all. What word or words meant the plus sign in my writing up here? That's right, added to, right? Added to. Aluminum foil is added to. That was the plus sign. Then we also have, hang on, I gotta sneeze. And we also have the arrow. No equal sign, because it does not mean equal. It's a story, it's a timeline, right? This symbol means turns into, or if you were to look at the way I did it up here, what words mean that change part? To produce, right? To produce. Aluminum foil and liquid bromine were produced aluminum bromide. This is the arrow here in this. So you can see that the chemical equation is just rewriting the words in a more efficient way. Now there's a lot of ways to say the arrow. And so as we go through others, we'll look and see if we can find what ways they're using to say the arrow. Okay, let's look at this reaction. Now this is a pretty cool reaction. Let's see if we can predict what's going to happen here based on the writing. Zinc metal is added to a solution of hydrochloric acid to yield a solution of zinc chloride and hydrogen gas. So I think what this is right here is the hydrochloric acid. They're going to add some zinc metal to this, and then a reaction is going to occur. It's obvious that a reaction is going to occur, right? The signs of a reaction are pretty. Look at that, definitely happening. Now I'm going to pause it here for a second because I want us to think about the chemical equation. Let me pause this for a second. Zinc metal, hence the S, right, which stands for solid, is mixed with hydrochloric acid, and there's the first time we've seen aqueous, right? So what does aqueous mean? If I go back to here, I told you I think what's in here is hydrochloric acid. Now it just looks like water, right? But it's not just water. It's hydrochloric acid. It's something that's dissolved in water. So AQ stands for aqueous. It means that chemical is dissolved in water. Sometimes people will say a solution of hydrochloric acid is used. It just means they have a little hydrochloric acid dissolved in water. Think about this. You have salt in your salt shaker. We would write it like this. NaClS, right? But aqueous salt is salt water, right? This is salt water. We don't write NaCl plus H2O. If we just write AQ after it, I go, oh, you have a salt water solution. So that's what aqueous means. Now, it's also important to understand that if you ever add water in a chemical reaction, like let's say we had water here, water is not aqueous because water can't dissolve in itself. Water, if you had it in a chemical reaction, would just be a liquid, right? So aqueous means something dissolved, like salt dissolved in water. Now, let's look at some other things that are going on here. So we know that aqueous means a solution. They added the chunk metal of zinc. And as we go, what do you think these bubbles are over here? Well, it's definitely something being made. Remember, there weren't bubbles in the beginning. It's something that's going to be a product. So it's got to be on the right side. These are the two products. Is it zinc chloride or hydrogen that's bubbling? It's definitely hydrogen because that's the gas, right? It's a gas that's coming from it, which, by the way, hydrogen is very explosive, so you wouldn't want to light a match around this thing. But you might wonder, where's the zinc chloride? Can I see that with my eyes? And the answer is no, you can't, because zinc chloride is aqueous. It's a solution. It's a salt, much like sodium chloride, that's dissolved in the water. And so we don't see it because it's just dissolved in the water. So some products you can't see with your own eyes. Now you can see in this reaction why chemists like to use chemical equations or chemical reactions, because writing it out takes so long. And yes, the chemical equation looks a little bit big, but at least it fits on one line. Now I did not put the state symbols in here, so let's see if we can put some state symbols in here. It says a solution of potassium iodide. All right, it's a solution. So right here, what state symbol goes for potassium iodide? It's aqueous, that's true. It's added to a solution of lead nitrate. That's aqueous too. To make lead to iodide as a precipitate, we're going to see what that means. That's a new word. And aqueous potassium nitrate. So that's aqueous as well. It's a solution. I don't think we're ever going to see this. I think these are all going to look like clear solutions because it's just salts dissolved in water. All right, now I want you to look back up my description here for a second and look down here at the chemical equation. You remember that a product needs to be something that's made in the reaction. So which of these four chemicals are products? And there may be more than one correct answer. Did you get these? These are products? Yep, everything on the right side of the arrow are products. They're the things we're going to make. The reactants are the things we're going to have to bring into lab. So these, we should see the chemist add these two. Okay? Now for us to really understand what a precipitate is, we need to see this reaction occur. So I want you to notice here in the beginning what I think is going on. This, I think, is a solution of lead nitrate. And you can barely see it, but they have a dropper in there. They're about to add a drop of potassium iodide. They both look like clear solutions because they're aqueous. They're salts dissolved in solution. We know we're not going to see the KNO3, but we're going to make lead iodide as a bright yellow. Well, watch. Isn't that incredible? That yellow stuff is lead iodide. It is a precipitate. What this yellow stuff is, if you look at it, it's a powder. You could actually filter this stuff. It's a powder, so therefore it's going to be a solid. So a precipitate is when a powder forms surprisingly when you create a reaction. And yeah, you could filter that stuff off. Now we don't see the KNO3. We don't see that because it's just dissolved in the liquid. But the lead iodide precipitate, which is a powder, we get to see really clearly. And so we know that that's a solid. Okay? Now, let me erase some of the ink from the slide. Well, actually, I'm going to leave it on there because I don't want to get rid of the state symbols. But we know the reactants are lead nitrate and Ki, and those were the things that the chemist brought in the beginning, and the products were the things that were made, including this yellow stuff. But when I look at the written form of it here, what I'm wondering is, well, what word or words in here mean the arrow? Let's see. Dropwise to a solution of lead nitrate. To make, I think that is the arrow. What word or words in here mean the plus sign? You could go for either plus sign. A solution of potassium iodide is added dropwise. I think that's the plus sign to a solution of lead nitrate to make, there's the arrow, lead iodide as a precipitate. And I think that's the other plus side. This chemical and that chemical, right? So you can see chemical equations much easier to write. But I don't want you to think that all chemical equations are difficult and have to be like done in a lab. Look at this one from the Royal Society of Chemistry. They're just talking about rusting. Now, if you look at my description of here of rusting, solid iron oxide is produced by the mixing of iron and oxygen. This is what the chemical reaction looks like. What is a reactant in this reaction? Yep, iron and oxygen are the reactants. Rust is the product. So you're going to see they're going to start with a clean metal plate of iron. There's the iron. The oxygen they don't have to bring because that's just in the air. And the product is iron oxide. We don't see it yet because it's a product. Now, they left it out in the rain and then brought it in to the lab to take pictures of it. And they time-lapsed it over a long period of time. And watch, in the beginning, there's no rust at all. because it's a product. It's going to get made as we go. So the steel plate, the iron plate, there's the rust starting to form. That red stuff is the rust, right? It's the product that wasn't there in the beginning. Yes, the plate in the beginning was a solid, oxygen. We can't see it because it's around, it's a gas. But the rust is also a solid. It's kind of a flaky powder, right? Now, the reason I bring this one up is I don't want you to think chemical reactions only occur in the lab. They occur everywhere, absolutely everywhere. We wouldn't be alive if we didn't have these reactions. So this is maybe not the most positive one because we often don't want things to rust. But most of the processes we use in our body to turn food into energy involve chemical reactions. So they're everywhere. But I also want you to look at this. Look at this sentence. What word or words in here mean the arrow? Mixing of. That is true. That means the arrow. But do you notice something weird about this writing? What word or words mean the product? Iron oxide, right? This is the product. Do you see how it's written first? Yeah, when you're doing a written description, solid iron 3 oxide is produced. Ooh, wait a minute. I got this wrong. This is not the arrow. Is produced is the arrow by the mixing of, that's the plus sign. But my point being is, do you see how the reactants are written at the end? Sure. You can tell stories in lots of ways. I got out of bed this morning. I ate breakfast and took a shower. Or I took a shower after I got out of bed and ate breakfast. You can switch the order around, and that's really important to understand about chemical reactions. The other thing to understand about chemical reactions is while you always have to have the product on the right and you always have to have the reactants on the left, you don't necessarily have to have the reactants in any order. Think about this. I mixed iron and oxygen gas to make rust, or I mixed oxygen gas and iron to make rust. You can switch the two reactants, but you can't put the reactants on the right side. That's important to understand. All right, so that was our introduction to chemical reactions, chemical equations, and chemical symbols.